Hello there guys, welcome back to another epic inexorable maths video. In this video we're going to find the moment generating function for a normally distributed random variable. Now we're going to use three important things in this video, so I've written them down and I just want to run them by you so that you know basically what you need to know in order to understand this proof or derivation. So first things first, the first bullet point, we need to know what the moment generating function of just any random variable actually is. So hopefully you're pretty happy with this. I've got like loads of videos on moment generating functions. So this is literally just the definition of what a moment generating function actually is. Next thing is the second bullet point. This is just the probability density function for a standard normal distribution, okay? You don't even need to know the probability density function for a general normal distribution, which is what we're going to find in the video. You only need to know the standard normal distribution, which is pretty cool. And the third one is basically the moment generating function of a linear function or linear transformation of a random variable x is given by this. And I've also got a video on this relationship or identity that I'll leave a link to in the description as well. So all of these things, I've already got videos addressing them, or they're just standard facts from basically from probability or statistics. So we're going to use these three things and I just want to run them by you. So the standard way of getting your moment generating function is to just directly do it basically. So what I'm going to do is I'm going to make a case to you of why I'm going to do what I'm about to do, because if you do the more direct way where you're just like, let's just do it, let's find the moment generating function of just any normally distributed random variable, let's just do it right now. That's of course again the expected value of e to the tx. And in the case of a normal distribution, I'll show you what it is, but this is what we're not going to do. But it would technically be this: the integral from minus infinity to infinity of e to the tx times the probability density function of just a generic normal distribution. That's going to be 1 over the square root of 2 pi times sigma squared times e to the power of minus a half times x minus mu over sigma all squared dx. Now, this, I mean, it is possible. It's not that bad, but it's quite bad. And so doing this integral is, it's one step away from an absolute nightmare, let's put it that way. So we don't want to do this. It's really, really messy. What we're going to do instead is we're going to find the moment generating function of the standard normal distribution, which I've written the probability density function of it right here. As you can see, it's not that much better, but it's significantly better, I think it's fair to say. And then we're just going to recall that a standard normal distribution can be transformed into any normal distribution via a linear function. Okay, we're going to do all of this, and it'll make sense if it doesn't make sense right now. And then what we're going to do is use this formula to basically so it prevents us from needing to do a really crazy integral. The integral will still be quite bad, but we're going to transform our standard normal distribution back into a normal into a generic normal distribution, and we'll see what happens. But what I'm saying to you right now is we're definitely not going to use all of this, because although it's possible, it's not nice. Okay, so the first step, as I said, is we're going to find the moment generating function for a standard normal distribution. Let's do that right now. So m sub z of t, because I'm using z here, is again, it's the expected value of e to the power of t times, in this case, z. The letter doesn't matter that much, but I'm using it because it's standard notation. And it's going to be the integral from minus infinity to infinity of e to the power of t times z times the probability density function for a standard normal distribution, which I've written down in yellow or orange over here. So it's 1 over the square root of 2 pi times e to the power of minus a half. And I've written this one in terms of x, but this one I'm going to write it in terms of z like this. Okay, so this integral is the one we're trying to do. Now, it looks almost as bad, but it's not quite as bad as the one that I drew a few minutes ago. So I am going to now just turn it back into x's because I don't really want to deal with z's. It just adds unnecessary complexity to the question. So let's just rewrite it in terms of x's because it doesn't matter what letter of the alphabet that you use. And actually, I mean, this up here, I've said dx. It should have been a dz, but it doesn't matter because now I'm turning it into a dx. So now this is the integral that we're trying to compute. So let's actually do it. We do have to do it directly. It's quite a difficult integral, but we can make it work. So we're going to take the 1 over root 2 pi to the outside. Then we've got the integral from minus infinity to infinity of e to the tx minus a half x squared dx. That's how I'm going to write it. So I'm combining the two exponential terms there. And then I've got 1 over the square root of 2 pi, integral from minus infinity to infinity. And basically my strategy, you might say, oh, can we do a substitution or something? No, basically, no, don't do a substitution. Basically, we will do a substitution, but not right now. Basically, the plan is we have to notice that this looks like something called the Gaussian integral, which is quite a famous integral. If you don't know about it, don't worry, I'm going to tell you about it. But what I'm going to do is I really want the exponent to just be something squared. I really want that. At the moment, it's like something minus something squared, which I don't want. So what I'm going to do is I'm going to write the terms kind of the other way around. So I've got minus a half on the outside of some brackets, times it by x squared, and then I'm going to have to do a minus 2tx here to make that work, okay? Now, it's not squared yet, of course, but we're going to get there. So this is equal to 1 over the square root of 2 pi times the integral from minus infinity to infinity of e to the minus a half. And now I can complete the square on it. So I can go x minus t squared minus t squared, close bracket, like that. I've completed the square on it, and you're going to see that that's helpful. That is very helpful. So this proof is not very like directly obvious how to do it. It's just about knowing, basically. Unless you're a genius, you're not really going to see this necessarily. Okay, and then t squared over 2 is a constant with respect to x, so I can take it out. So I can rewrite this as e to the power of t squared over 2 divided by the square root of 2 pi times the integral from minus infinity to infinity of e to the power of minus a half times x minus t squared dx. Now I can do a substitution, okay? So what I'm going to do at this point is I'm just going to remind everyone about the Gaussian integral. It says that the integral from minus infinity to infinity of e to the power of minus x squared dx is the square root of pi. So if I can do a substitution that basically gives me this integral, I can just rewrite the whole thing as the square root of pi. If you want to know where this comes from, I've got a video on it. I'll leave the link in the description, but it's a very, very, very famous integral. So continuing on, what we're going to now do is do a substitution. So I'll do it here. I'm going to let u equal, let's think about this, because I'd really like the power to just be u squared. That's what I'd really like. So if I kind of close the bracket here instead, then in order to, because obviously the 1/2 would become a quarter, which I don't want, that is a 1/2 on the outside. So what I need to do if I'm going to move the bracket is that needs to be 1 over root 2. And then I can, hopefully it's fairly clear, I can let u equal 1 over root 2 times x minus t, okay? And that will then end up replacing the whole thing with, and I'll end up getting e to the minus u squared, which is what I want. We can also see that du dx, because we're treating t as a constant, is just going to be 1 over root 2, which means that du is going to be 1 over root 2 dx, which means that dx is going to be root 2 du. So what we can do is we can replace the limits. Hopefully it's clear to see t is just a fixed number, so it's finite. So that means that the limits are still going to be minus infinity and infinity. And then I've got e to the minus u squared, and then dx is root 2 du. Okay, and then you can see that the root 2s, this root 2 and this root 2 are going to cancel out. And what I'm going to end up with is I'm going to have e to the power of t squared over 2 divided by the square root of pi. And again, we can see that the integral that I'm dealing with is exactly the Gaussian integral. So it's the square root of pi as well. And obviously these cancel out. So I end up with e to the power of t squared over 2, just like that. So what we have shown so far, we're not done yet, but what we've shown so far is that the moment generating function of a standard normal distribution, that is a normal distribution where the mean is 0 and the variance is 1, is just e to the power of t squared over 2, which is a really nice, simple answer. Now again, we're almost done, but we're not exactly done, because we want the moment generating function for any normal distribution, one that has a mean of mu and a variance of sigma squared. So now what we're going to do is we're going to recall one more thing. Okay, so I'm going to write one more thing down. We want to recall that the standard normal distribution is linked to any normal distribution via this formula or this transformation. Okay, so a standard normal distribution is just any normal distribution that you want minus its own mean divided by its own standard deviation. This is a very, very well-known formula, very simple formula. And if we rearrange it ever so slightly, we see that sigma times z is x minus mu, which means that x is equal to sigma z plus mu. Why is this important? Well, remember, I've written this down at the top as well, but I'm just going to write it down here so we can have it on the same page. But the moment generating function of a linear transformation of a random variable like this, there we go. The moment generating function of a linear transformation is given by this formula. And again, I've got a video on this that you can obviously check out if you want, if you don't know where this comes from. This just comes from simply the fact that if you write down the moment generating function in terms of the fact that it's the expected value of e to the random variable times t, this just pops out. It's not difficult derivation. But the point is that we're trying to find the moment generating function of a linear function of a random variable. Well, we already know the moment generating function of that one, right? So let me explain what I mean, right? So if I want the moment generating function of sigma z plus mu, remember this is just any normal distribution or any normally distributed random variable. So this is exactly what we are looking for of t. This is nothing more than e to the power of mu t times the moment generating function of just z, but instead of t, it's sigma t, okay? And again, all I'm doing here is I'm just using this, all right? Now, we already know what this guy is, or we can easily get it. So what we have is that the moment generating function of sigma times z plus mu of t is e to the power of mu t times, and again, this guy here, this is just e to the power of, and every time you see a t, you've got to replace it by sigma t. So we've got sigma t squared over 2. And in other words, that's e to the power of mu t plus sigma squared t squared over 2, like that. And that's the final answer, okay? Because again, this here, for a standard normal distribution, if you times it by some number sigma and you add mu, that is just a normal distribution that has a mean of mu and a variance of sigma squared. So this is the moment generating function of just anything. And this is when x is distributed normally with a mean of mu and a variance of sigma squared, like this, okay? So this is basically what we're looking for. So we've done that. So that is, I mean, it was, it was long. Let's just recap what we did, because we did a lot of things here, but that is all there is to it. So just as a recap, what we did is we found the moment generating function for a standard normal distribution, because it is much easier to do that integral. The algebra is much easier, so it is worth doing that. We used the probability density function of the standard normal distribution. We did a bunch of algebra. What we did is we simplified it and we completed the square in the power, and that is because it's a very difficult integral to do without. It might even be impossible. I don't know, but definitely the easiest way of doing this is to turn it into basically the Gaussian integral, which is what we've done. We did a substitution that really helped us out there. We recalled this orange result here, this yellow result, that the Gaussian integral is just the square root of pi. We ended up getting the Gaussian integral, we replaced it with the square root of pi, and everything cancels out, and you get e to the t squared over 2. And then we recalled that the moment generating function of a linear function of a random variable has this property here. And we've been like, oh, okay, well, any normally distributed random variable is just a linear function of the standard normal distribution. That's just a property of the normal distribution. And so we exactly use this. Again, derivation of this guy in the description. And we ended up getting boom, 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 that's our moment generating function there. And that's for any normally distributed random variable. So guys, stay tuned for more moment generating function videos. We've got loads and loads and loads of functions coming up. Chi-squared distribution, Laplace distribution, Cauchy doesn't have one, but anyway. And you're going to see all of that coming up very, very, very soon. So if you enjoyed the video, then obviously guys, like, share, subscribe with your friends, family, and even your enemies. And I'll see you in the next one. Cheers.